Welcome to Study Loop.
This is the answer to Chapter 21, problem number 84 from the Smith Organic Chemistry textbook. And this problem says an unknown compound C of molecular formula C6H12O3 exhibits a strong absorption in its IR spectrum at 1718 wave numbers and has the given proton NMR. What is the structure of molecule C? Okay, and so given this formula, the first thing to do, as always, when we're given a formula and asked to find a structure, is to calculate the hydrogen deficiency index. And so it's going to be 2 times the number of carbons, which is 6 here, plus 2, minus the number of hydrogens, which is 16, and then all of, oh, geez, it's not 16. I apologize. I was doing the math in my head, and I was like, that's a negative number. So it's 12, and then all of that over 2, and that's our HDI. And so 12 plus 2 minus 12 is 2, and then divided by 2 is 1. So we have an HDI of 1. So there is one double bond or one ring in this molecule. So the next piece of information we're given is IR. And so at IR, we have a peak at 1718 wave number, and that should tell us carbonyl. So C, double bond O. So that also fits with our single degree of unsaturation. And so that's good. So then we need to look at the NMR. And this NMR is given to us. The integrations are not given to us as nice, easy numbers. So what we have to do in order to solve what these integrations actually mean, we need to add all the integration numbers up, divide by the number of hydrogens that we have, which again is 12, not 16, and then divide each integration by that number. So that's going to look like this, right? So we have 7. The next signal is 40. The next signal is 14. And the next signal is 21. So all of that added together is going to give us 82, right? 8, 42, 82. Yep. So 82. And when we divide 82 by 12, which is the number of hydrogens that we're looking for, we get 6.8. And then we need to divide each of the signal numbers by 6.8. So 7 is going to equal roughly 1. 40 divided by 6.8 is going to equal so 40 divided by 6.8 is going to equal roughly 6. 14 divided by 6.8 is going to equal close enough to 2. And then 21 divided by 6.8 is gonna be a 3. Okay, and so that's our integrations there. And then so rather than cramming stuff in, I'm just going to start a new page to deal with our NMR data. Okay, and so it may be helpful to write each signal out, and I'll just go right to left. So signal A, we have a singlet at 2.2 that integrates to 3 protons. Signal B, we have a doublet at 2.7 that integrates to 2 protons. Signal C, we have a singlet at 3.2. 3.2 that integrates to 6 protons. And signal D is going to be a triplet at 4.8 that integrates to 1 proton. Okay, and so we also know that we have a carbonyl somewhere in this molecule, right? From the HDI and the IR taken together. And then from our singlet at 3.2, so signal C, right, with 6 protons, taken in conjunction with the fact that there are 3 oxygens in this molecule. So I'm thinking for signal C, I'm thinking 2 methoxide groups, right? So 2 OCH3 groups, because that would account for the fact that they're singlets. They have no neighbors. They're bound to an oxygen. It accounts for the, pardon me. It accounts for the chemical shift of 3.2 ppms, which is pretty far downfield, but is typical for what you expect for protons on a carbon bound to an oxygen. And then it accounts for 6 of them. So I'm thinking 2 methoxides there. The other thing that jumps out is we have a proton, 1 proton, giving rise to a signal by itself. It's a triplet, and it's at 4.8, which is far downfield. And so what I'm thinking off the bat is we have, as I said, 1 carbon that's going to have these 2 methoxides coming from it. And it's going to have whatever else on the rest of the molecule, but it's also going to have a single proton there. And so that's going to be HD. And then these protons are going to be HC. And so then we just need to fill in the other pieces of this molecule. So we have a singlet at 2.2 integrating to 3. So that's probably a methyl group, CH3. It's a singlet, so it has no neighbors. And then we have a doublet at 2.7 integrating to 2 protons. So that's a CH2 like that. Both of these 2.2 and 2.7 are somewhat downfield. So what I'm thinking is that we have our ketone. Well, sorry, we don't know it's a ketone yet. So we have our carbonyl, and I'm thinking that this methyl group is on one side of it, and this methylene group is on the other. And so what that would look like would be like this. Right? So the chemical shifts would account for these protons being alpha to this ketone. And the integrations make sense, and the splitting patterns make sense. Right? So let me go ahead and fill them in. So these protons would be B. They're a doublet. They have 1 neighbor, D. D is their only neighbor, so they're split to a doublet. They in turn split D to a triplet. And then this is A, these 3 protons, and they fit the characteristics of A. They're a singlet. They have no neighbors. They integrate to 3, and they're at 2.2 because they're alpha to a ketone. And so, yeah, so all of this spectral information makes sense. And this is, in fact, the correct answer to this problem. And yeah, so that's the answer to chapter 21, problem number 84.